Welcome back to the Cycle World Podcast. I'm the editor-in-chief, Mark Hoyer, and I'm with Kevin Cameron, our technical editor. We have a topic this week. Kevin will call it acoustic supercharging, and I will call it the origin of the expansion chamber. So what we're going to talk about is, where did the two-stroke expansion chamber come from? The minds of geniuses, of madmen. So it's a topic, you guys have been loving the two-stroke stuff, the TZ750 and the RD350, and we thought we'd get into a detailed conversation about the origin of the expansion chamber. Before we get started, we want to thank Octane Lending for sponsoring this episode yet again. You can click a link down in the description of this video, and you can shop for a motorcycle and see about getting financing to assist you in your purchase if you require it. So click that link and check it out. Even just clicking on it would be a big help for us. The other thing I have to bring up is some of the comments, or let me say one comment that is near and dear to my heart. It's King Broslaw is his name. He said, this is for all you on the streaming services. When are you going to tell the people listening via streaming services about your rad mustache? Friends, I have a mustache. And it's pretty, anyway, we appreciate the humor there. And I'm also glad it's flannel weather here, so you can see flannel companies, people are watching. I was recognized at Road America driving a golf cart by a viewer who said, "I recognize you because of your flannel." Pretty awesome. All right, let's do this, Kevin. Acoustic supercharging. So we all are used to expansion chambers that have a head pipe. They have what you would call the divergent cone,
or a megaphone.
Megaphone. Yeah. Yep, and it swells up into a ball. Big thing. It's like a snake that's eaten a rat, and then it tapers back down with the convergent cone, and then it goes out a stinger, or we hope a muffler, because they sound pretty nice with the right muffler. Sounds like beautiful popcorn. And so we didn't always have that. Two strokes were lauded for their simplicity, and but they didn't make any power when they were first put into motorcycles. So talk to me about that, Kevin. You may know something about this.
I might. Well, first thing is that when the internal combustion engine, the idea of burning the fuel in the cylinder rather than under a boiler full of water, was put into real form, the ideal was the steam engine, which is not a 4-stroke or a 2-stroke. It has 2 power strokes per stroke because steam is admitted at both ends. The piston rod goes through a seal gland on one end, and the other end of the cylinder is capped by a plain cylinder head. So they didn't want the idea of taking 4 strokes to get 1 power stroke didn't even occur to the early workers. So 2 strokes were very common in early internal combustion engine development. And a lot of them were so pitiful. They were trying to use part of the stroke to fill the cylinder and part of it to produce power, and they ended up with almost nothing. And of course, many ideas start out that way. What is now the semiconductor business can put billions of switches on a silicon chip, whereas before, this business started out with mechanical relays and then advanced to vacuum tubes as a means of switching. And those things were huge. They had hardly... And hot, yes. Especially air-conditioned rooms. Anyway, the 2-stroke idea got a lot of plays in the early days before Otto had his explosive introduction to the success of the 4-stroke. When
his
Otto
cycle.
Otto, O-T-T-O, yes.
Yeah.
And like many men, he was fortunate to have an understanding wife. He was frightened by the violence of this thing. I think he'd given it a little bit too much compression. After all, it was the first one ever. And his wife, when he got home, listened to his tale, and she said, look, just sit down. I'll make you something nice to eat, and tomorrow you can straighten this all out. And he did. He did. But the essentials of this two-stroke engine are these. You imagine a piston at top dead center with mixture, fuel and air compressed above it. A spark or other means of ignition sets it alight, converting it into high-pressure gas. The high-pressure gas pushes the piston down. If there's a connecting rod connected to a crankshaft, it can accelerate the crankshaft. If the rod connects to a water pump or any other useful device like that, nothing rotates. But the piston is on its way down, being pushed by the expanding gas. Doesn't get too far before the pressure in the expanding gas drops to a point where it can hardly push the friction of the piston rings. So at this point, it makes sense to open the exhaust port, even though there's still a little pressure in the cylinder. So there's a hole cut in the cylinder wall. And as the piston uncovers the top of it, what the German engineers called Auspuff occurs, outpuff. And when the pressure in the cylinder has dropped by means of this process, which we call blowdown, some other means of pumping delivers fresh charge to the cylinder through one or more fresh charge ports. Now, the problem is the cylinder at the bottom of the stroke is still filled with exhaust gas, although at atmospheric pressure. So by shooting in fresh mixture, we're going to be diluted by exhaust gas and thereby lose power. So very quickly, everyone devoted a lot of thought to ways to let the fresh charge enter without quickly mixing and being completely diluted by the exhaust gas. And we've all seen deflector piston two-strokes. The top of the piston has a wall across it on one side. It may be a curved wall or fence. This is the deflector. On one side of the piston are the exhaust ports, which in those days took the form of 3 or 4 round drilled holes because it was easy to produce. 180 degrees from that exhaust port or array of ports was the fresh charge port or ports. And they were a bit lower to allow the exhaust to blow down the pressure in the cylinder. And a rotary blower, a piston blower, or some other form of blower would then push fresh charge in through those ports. They would hit the wall, the deflector on the piston, and be guided upward, hit the cylinder head, flow over in reversing direction down toward the exhaust port. And this, by having the flow attached to the rear cylinder wall, then to the cylinder head, and then to the exhaust cylinder wall, protected it to a great extent from exhaust dilution. Still, it was a feeble scheme. And the extra surface area added to the piston by the deflector caused the piston to run really hot. The central problem of all two-strokes is that they're heated. The piston is heated twice as often as a four-stroke piston. So the problem is to cool the piston. And this has remained a theme throughout all of history of the two-stroke.
How many two-stroke pistons have been holed in this world? How many?
Well, the early schemes all depended on the idea of blowing fresh charge into the cylinder so that it would push the remaining exhaust residuals out.
And when we're talking about that, we're talking about a mechanical supercharger. We're
some
talking
kind
about
of blower. Some kind of blower.
blowing it physically, not relying on just like your normal 4-stroke to have some vacuum pulling it in. It's actually being forced in through a pump of some kind.
People who are familiar with 671 blower that used to be used on so many top fuel drag cars, that blower was used on a 6-cylinder Detroit diesel, 2-stroke diesel, and mounted on the side of it, and it supplied air pressure to a chamber that surrounded all of the scavenge ports in that engine. The exhaust ports were in the head, and the fresh charge ports were a ring of holes at the bottom of the stroke. So this was another step in segregating fresh charge from exhaust residual, because it's leaving from one end, entering from the other end, so it reduces the opportunities for mixing. Then somebody had the idea, let's take that cylinder with the exhaust on the top and the fresh charge on the bottom and bend it in the middle and give the 2 cylinders that result a common combustion chamber. I think Sears Roebuck used to sell Puch motorcycles and scooters that had this strange 2-cylinder, 1 combustion chamber, 2-stroke engines. I think they had a Y-shaped connecting rod also.
Oh yeah, it's a thing of beauty. If you've never seen that, the Y-shape, it just looks, to a person who's worked on regular old motorcycle engines with your typical connecting rod. When you see a Y-shaped connecting rod, you just think, what horror is this?
who could have conceived such a thing? Well, the idea of uniflow scavenging, exhaust leaves from one end of the cylinder, fresh charge comes in at the other, continues to this day as the power plant of world trade. Enormous marine diesels making up to 120,000 horsepower. Powers all the ocean ships. But back to practicality. How can we make a motorcycle? And how can we get rid of the excess heat absorbed onto the piston by that deflector? And a diesel engineer named Adolf Schnerle had this idea. He said to himself, okay, here's the exhaust port at one side of the cylinder, and on either side, we'll make transfer ports that are aimed away from the exhaust at the opposite cylinder wall, and the flow from them will hug the piston so that, again, the flow will be attached to a surface, flows across the piston to the rear cylinder wall, up across the underside of the head and down to the exhaust. No deflector. A flat-topped or very slightly domed piston. It was a great success. This was called Schnerle scavenging. And it didn't require U-shaped cylinders or shared cylinder. Here's mine. No, mine. And it didn't take all the power out on the exhaust piston. So, but again, the problem with this engine was, how are we going to pump fresh mixture if we don't want the complexity of a blower? DKW had built very powerful twin piston racing engines in the 1930s. They claimed they could hear them on the mainland of Britain all the way from the Isle of Man. They used, at first, a giant piston blower, a reciprocating piston. Then they used a rotary blower. When the war ended and the International Motorcycle Federation wrote new rules for racing, they allowed 2-strokes to have the same displacement as 4-strokes. And the reason they did so was, one, they were just such pitiful, smoky pieces of junk. And two, they used the underside of the piston as their scavenge pump. When the piston rose, it created a partial vacuum in the crankcase. A carburetor connected to that crankcase flowed mixture in. And when the piston started down, its skirt closed off that carburetor port and compressed very slightly the mixture in the crankcase, allowing cup handle shaped ducts to transfer the mixture in the crankcase pump. Yes, like that.
Much like this coffee cup. I'm holding a coffee cup up, folks, to show, this is descriptive audio again, to show this, show the handle, the curved handle. That's where the transfers basically are on the sides of the cylinder. And that'd be a whole discussion in and of itself, aiming which direction the transfers will point in the cylinder. That's later in this discussion.
Many workers, many hands. This whole process took from 1949 until the two-stroke dominated all FIM classes in 1975. So that was a good long time in development. But the FIM, the International Motorcycle Federation, gave the two-stroke even Steven displacement with the four-stroke because it couldn't pump any more than its own displacement by using the piston, the underneath of the piston, as a scavenge pump. So this engine, it's hard to imagine a simpler engine. And DKW produced hundreds of thousands of RT-125s. You can see one in the Barber Museum down in Alabama. And it produced about 4 horsepower at 4,500 RPM. So this was no hold on to your hats machine. This was minimum motoring. But the presence of the Luftwaffe in so many parts of Europe meant that these motorcycles were loaded into the bomb bays of any aircraft that would carry them, because men in the soldiery always need cigarettes and beer. And if you've brought a little motorcycle with you and you have access, legal or illegal, to a source of fuel, you might be able to scare up some of those necessities. So after World War II, it was the most copied motorcycle ever. There were Spanish copies. The British copy was called the BSA Bantam. The American copy was the Harley Hummer. And several Japanese makers started out, and this includes Honda, building two-strokes based on the RT-125. Just worked out that way. Because what the world needed in 1945 was a way to get from A to B without having to walk it the whole way. So now began the problem. People in East Germany, of course, being persons of analytical mind, began to consider the problem of racing. The war was a drag, and post-war rationing isn't much better, so we'd better go racing in order to take our minds off these other problems. And a fellow named Daniel Zimmerman began tuning RT-125s, and he soon found that a rotary disc with part of it cut away made an excellent intake valve, because you could have any timing you want. If you used the skirt of the piston to uncover an intake port, that gave only symmetrical timing. If it was 101 degrees before top center, it was 100 closed, 101 after. So that was Zimmerman's contribution. Rotary disc valves had existed before. The Sun Vitesse motorcycle had one. But he gave it a racing application. He also turned the cylinder around so that connecting rod side thrust pressed the piston against the exhaust port, improving the seal and the cooling of the piston. So at a point, the official impetus was put behind a company called IFA, and they thought IFA should go racing. And so the Stasi went and had a conversation with Mr. Zimmerman. They said, you will hand over all notes, prototypes, racing machines, etc., and all parts, and you will forswear contact with motorcycles for the rest of your life. Agreed? He readily agreed. What choice did he have? And so development of the two-stroke at IFA, which shortly became MZ, Motorrad Zschopau in East Germany moved forward. Meanwhile, DKW in the western part of Germany, was also racing two-strokes. And in the late season of 1951, an engineer named Erich Wolf decided that he was going to look into the question of why two-strokes don't make a lot more power than they do. He knew that many racing two-strokes had a header pipe that came out of the exhaust port and went to a megaphone. And a megaphone is basically a means of turning a positive pressure wave, which is the Auspuff or blowdown, reversing its sign. And by making a megaphone, you presented this pulse to a larger area of atmosphere so that the expansion pulse or low pressure pulse went back up the pipe and into the cylinder. Now we're not only using the scavenger pump to push fresh charge into the cylinder, we're also creating a partial vacuum in the exhaust pipe, which is inviting all those hot buzzing molecules. Wouldn't you like your freedom? Come this way. So this double whammy ran into a big problem because the engine revved up until the amount of exhaust lead, the degrees between exhaust opening and transfer opening, became too little to let the pressure out in time for the transfers to start pumping fresh charge in. Well, let's raise the exhaust port then. What happened then was that with the megaphone exhaust and the piston is now coming up to close the exhaust port. It's already closed the transfers. Now the exhaust port is poking up above the piston. It's pumping the mixture back out. And the exhaust pipe with its megaphone is still going, come hither. I've got something for you. So this meant that in the immediate post-war years, the two-stroke single, let's say a 125, was stuck at between 8 and 12 horsepower and about 7,500 to 8,000 RPM. If they raised the exhaust port, they lost charge. If they ran the exhaust port at the normal 17 degrees or so, the engine was weak and only made this very limited power. Now what? So Wolf had no doubt had a look at books such as this. This is Schweitzer's Scavenging of Two-Stroke Diesel Engines, and there's a special chapter in here. This is a 1949 book on the use of exhaust energy as a means of improving scavenging. 1949. Before that, Michel Cadenassi, who had proposed the use of the exhaust to generate low pressure in the cylinder to invite the fresh charge in. So there was a lot of discussion going on about this. Erich Wolf was not a gyro gear loose trying one crazy thing after another until he stumbled across the truth. He was working with definite ideas. His idea was, we'll put a stopper on the end of that megaphone so that it doesn't lose as much fresh charge. And the stopper was a little abrupt, so instead they pulled the middle of it out to make a convergent cone. And that's what ran on DKW's 125 factory racer at the end of the 1951 season. Well, did DKW become world champions overnight? They did not. They stayed with the original 17 degrees of blowdown, even though they had a means of preventing charge loss. And this was so radical, imagine this. DKW's three-cylinder 350 turning 10,000 RPM, maybe even a bit more, unable to defeat Moto Guzzi's rather vintage-looking horizontal single-cylinder four-stroke. Embarrassment. How can this be? Well, along came Walter Kaden, who'd worked at Peenemünde, the rocket research center of Germany during World War II. We don't know whether he emptied trash cans or whether he was involved at some level in the thinking process, but he'd certainly been exposed to the roar and the drone. I think of him as not the inventor of the modern two-stroke, but as the systems integration officer. His job was to bring together the rotary disc intake, Daniel Zimmerman's other big invention, which was very tiny needle rollers in the big end of the connecting rod. They lived, bigger rollers failed. They turned blue and squashed out into sharp-edged pancakes. I think what Kaden's people were able to do, he worked with one or two others, was to discover that they could extend the blowdown. They could raise the exhaust port without losing charge because they had the counter cone. The Germans called it a Gegenkonus counter cone to stop reflecting back a negative wave, which would tend to pull exhaust or tend to pull fresh charge out of the cylinder, and substituted a counter cone which would reverse the signal again and send back a positive wave.
Shutting the gaseous door.
Yes, absolutely. Yeah. Acoustically providing an acoustic door. And it did more than that, because if you imagine what's going on in the cylinder, the suction, if you will, from the megaphone part of the exhaust pipe is pulling fresh charge into the cylinder and into the header pipe. And now the piston is rising, it's closed off the transfers, and there's still exhaust opening left. Now this pressure wave comes back from the counter cone, and it pushes that fresh charge in the header pipe back into the cylinder. The exhaust port closes. The cylinder is now much better filled with fresh mixture. There's a lot of exhaust gas in there still, but there's been a gain. So by 1958, Walter Kaden of MZ was able to build a 125 single that made decisively more power than the best 125 four-stroke singles. And that company's twin-cylinder two-stroke, 250, was making 48 horsepower, which was certainly competitive. The problem was that East Germany was economically feeble at this time. It was not a post-war return to health dynamic economy like West Germany. And so Kaden's R&D program was himself and one or two other fellows. And whatever funding they could wheedle out of their Stasi advisors, that was up to them. So there were some stunning results, really wonderful performances from MZ motorcycles. But in the meantime, these new two-stroke concepts fell into the hands of companies that had serious R&D power, namely Yamaha and Suzuki. I'm going to leave out of this discussion all of the talk about Ernst Degner defecting to the West with his all kinds of drawings and cylinders and so forth stuffed under his shirt. That's another matter entirely. But what happened was that once Yamaha got hold of these ideas, They quickly mastered the problems that MZ had been unable to, namely piston and cylinder metallurgy. They created controlled expansion alloys that did not immediately seize when they made more than 4 or 5 horsepower. And that was essential because one of the Suzuki engineers described their problem. He said, "Our pistons swell like a cake in the oven." I always loved that.
Oh, yep. Food analogies can't miss.
Yep. But in 1962, at Spa-Francorchamps in Belgium, riders Sunako and Ito on Yamaha RD56 machines just steamed away from the Honda 4s. They just left them for dead. And Honda engineers realized, oh, this is a big problem. We're going to need more cylinders, more RPM, more everything. And the result, the direct result of Sunako and Ito's 1-2 was the Honda 6, the 256, because 4-strokes combustion pressure, unsupercharged, is limited by the atmosphere's pressure, 14.7 psi. So that's fixed. Displacement is fixed. The other variable among the three that make up horsepower is RPM. So Honda had to set sail for 20,000. Meanwhile,
thank goodness. I mean, what a thing to
what a sound.
Competition pushing. Yeah, it pushed 4 strokes. And, 2 strokes kept going, but it pushed 4 strokes, and we got some beautiful things out of it. Tiny little pistons, teensy little spark plugs, tiny little valves, all going,
yes,
making a symphony of inline sixness.
Pistons performing their stroke 300 times per second. Delightful.
Amazing. I think I want to do a podcast sometime on the inline 6 and why I think it's the perfect engine, but that's me.
Well, no question that it is a very distinguished engine.
It is magnificent.
Once they got it working, and it took them a while, they introduced it at Monza in 1964, and not until Halewood got on the 256 and the 297 6-cylinder 350, they became, Halewood was unbeatable. He won 250 and 350 in 1966 and 67. So that was a black eye for the 2-stroke folks. Anyway, what happened, of course, was that these engines were just refinements of the original Daniel Zimmerman engine with 3 transfer ports. The ones on either side of the exhaust port plus one opposite the exhaust, sort of aimed up at the cylinder head. But soon, Yamaha and Suzuki began to refine the shapes of exhaust pipes and the shapes, direction, and number of transfer ports. And the result of that work, that intensive work over a period of years, was that when the 2-stroke era ended with the coming of MotoGP, 125 2-strokes left the scene in 2012, I think. They were making nearly 60 horsepower, or 12 times the pitiful smoky power of 1949.
Amazing.
And the shapes of things had changed a great deal. As Dutch tuner and engineer Jan Thiel has said, we really started to make serious power when we adopted the cup handle style transfer ports rather than the more common ones, which went up each side of the cylinder and then suddenly turned at 90 degrees and attempted to enter the cylinder abruptly in that way. And of course, what that does is it's just like in a four-stroke intake port. On the far side, the flow is high velocity, highly efficient. On the near or short side, there may be almost no flow at all because the turn that you're trying to make the air do is just too abrupt. It can't do it.
You're almost making, after the turn, you're effectively reducing the size of the port because it's blocked by all the momentum.
Yes,
is
all the flung to the outside. Yes.
So we're talking about a curved transfer that's like the cup
graceful.
Coffee graceful curve, because air needs that. Air has mass and momentum and all the things that happen with making it flow at near supersonic speed sometimes. And having that curve allows the air to do its thing, whereas the old transfers or the ones on like a parallel twin, they're 90 degrees, they are sharp turns, and it just doesn't flow right. And it just doesn't give you what you want.
And
up
this
to a
is
point
why,
works, but then,
this is why a big step forward for 250 twins in GP racing was to take the two cylinders and swing them apart 90 degrees. That made room for all the transfer ports all the cup handle transfer ports you could want.
Kevin took his fingers and made a parallel twin, and then he crossed them over to make it a V twin. And then you had room on the sides of the cylinders instead of having them smashed up against each other. You had room on the sides of the cylinders. Put those transfers in to make it flow. I want to go back to the basics of what we're talking about to help people visualize. A two-stroke has a solid cylinder head with a spark plug usually centrally located in a little dome. A lot of squish. And then
a ring of squish.
A ring of squish, which is just squish is an area of the cylinder head that is really close to the piston. When the piston reaches top dead center, it might be, if you're fancy, it might be 28 thousandths of an inch, the clearance. Yep. Very, very close. And if you're on
7/10 of a millimeter.
Yeah, and if you're running your pre-unit Triumph with aluminum connecting rods, you're probably not going to go under 40 thousandths of squish. But you're making the piston get really close to the cylinder head, and they call it squish because it squeezes the mixture out from the edges of the piston to where the spark plug is, especially in a two-stroke, centrally located. Bang, and it's right where the fire is being lit. So that
gives it a last-minute stir.
And it, homogenizes it, mixes the fuel and the air really well, and it jams it right up against the sparking device, which is great. So that's all we have. The two-stroke is the piston is the valve, essentially. We can talk about reeds and all the other things, but if you just put the piston at the bottom dead center, and blew through the carburetor, it's going to go in and out. It's just going to, you have an exhaust port and you have transfers, and there's nothing to stop it. The piston has to block those. And that's the whole trick with two-stroke timing, is when is the exhaust port open, unblocked by the piston? When are the transfers unblocked? Because you have to close that off. The only time the engine can make power is when the valves are closed, right? Yeah. So it's, and the piston is the valve here in this case. And so
yes, it is.
This is the whole trick. And, Kevin's talking about mixture firing into the cylinder and going out the exhaust port. If it's not timed right, and if you don't have the expansion chamber sending a pulse back to shut the door, and to do it, to open it and to invite it out, and then to shut it to keep.
This is the reason for the ring ding idle, which which nervous four-stroke enthusiasts like to make fun of. Because what happens is, when the engine is operating on very low throttle, you're squirting a small volume of mixture into a cylinder filled with exhaust gas. Is the fresh charge anywhere near the spark plug when the spark occurs? Probably not. Well, another stroke, and it will have squirted in a little bit more fresh charge. Oh, that time there wasn't any near the spark plug either. A third revolution and a third injection of fresh charge. Oh, pop! It fires weakly. And so it takes several revolutions of the crankshaft to accumulate enough idle mixture in the cylinder for the spark plug and the mixture to be in the same place. So it sits there going pop, 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 and does not give you an inkling of what will happen at Daytona. An amateur-built motorcycle, that of Nick Rikiki, who delivered orange juice in New York City as a means of income. He went through the timing traps at 183 miles an hour on his TZ750, operating on this foolishly simple principle, which had been so refined that it worked quite well over a narrow range of RPM.
Well, that's the real point here, is that this acoustic supercharging is tuned to make power. It can't work across the entire, I mean, without, what would you do? They tried many different things to change the waves, like water injection to change the density of the exhaust.
They added resonators.
They started, they started moving exhaust ports. That was the power valve.
Eyelid exhaust ports, yes.
Yeah, and so that was an attempt, because in the strictest mechanical, you put it to me when we were porting my RD 350, is that whatever it was, we had talked about the power band and I wanted torque, and you said, yeah, my engines have always had torque, and you were talking about I was talking about, like, oh, I'm building a street motor, it's 4,000 to, or it's 5 to 7, I want, this nice strong mid-range torque, and you're like, 5? Like, you just looked at me like I was insane. And because you were making whatever it was, 6 to 10 or 7 to 10 or something like that.
Yeah, it was 7 to 10.
7 to 10.
Pretty much.
So between 7 and 10, you said it's time to cut wood. That's when, that's when the motors, that's when the tuning of the
everything's in step.
Yep.
Yeah.
All the waves are doing exactly what you want them to when you want it to happen. And you're pulling in a tremendous amount of fresh charge, and then you're pushing it back when the wave, if it's coming out the exhaust port a little bit, that wave comes and knocks it back in there. And that's when you're making all the power. And you can expand that a little bit with power valves and other things, but really it's just time to cut wood.
And the thing about this is anyone can do it. And that was the point of the late Gordon Jennings's book, Two-Stroke Tuner's Handbook. It basically said, here are a few simple ideas and a few elementary numbers that will enable any person of curiosity, with any talent, with any manual dexterity, to have a fast two-stroke motorbike. This is not a matter, two-strokes were not developed by mathematical models. Mathematical models may have helped years later, but the basic work was what the chemists call combinatorial analysis. Try everything. There were two guys in the basement, I don't know whether it was HRC or a previous organization, whose job was to get the horsepower out of engines that the engineers had finished designing. And you can bet that some of those new designs came into their department and they looked at the cylinders and then they looked at each other. It was like, what? But they quickly got to work trying lots of different exhaust pipe dimensions and transfer port aim, transfer port size, transfer port timing, until they got a glimmer. And I once had a phone call from a man who was participating in grass drag racing on snowmobiles. And he said, I'm almost there, but I'm not there. Can you help me? And I said, well, one of the things is that mixture that is caught in the squish band burns late. Because flame doesn't transfer into a 28 thousandths gap very rapidly. So you may be using too much squish, too wide a squish band. Unfortunately, the only way you can vary this is to make different sets of heads, all with the same squish clearance, but with various widths of squish band. And I described how he might do this. And I didn't hear from him for several months. And he called me and he said, I'm now the dominant force in my sport. Because he was willing to make those repetitive experiments until he got somewhere. And he got where he got to was the top. And there were lots of people messing with two strokes. Kel Carruthers messed with them. He's the one who teamed with the late Don Vesco in 71, I think. And he said, Don had this primitive dyno back in a storeroom somewhere, and I got the thing out and set it up and built a test engine that I could put one cylinder on. And he said, I started finding things out. And he found things out to the point that when Kenny's 250 was out qualified in 1976, Kel must have said, oh, all right. And he shortened the header pipes 20 millimeters in each exhaust pipe. He took 25 thousandths off of the cylinder head and recut the water seal groove. These were liquid cooled TZ250s. And he raised the exhaust port and widened it a millimeter on each side. Now, when you do that, those cylinders were chrome plated. Today, we have Nicosil, which is more durable. But with chrome, you cut it, it means a 900-mile cylinder becomes a 300-mile cylinder. But what do we want? Beautiful cylinders or races one? You know, it's like now with saving the planet. You want to save the planet? It's going to cost you. Those solar arrays aren't free. Well, Kel knew that making those changes would completely transform the stock engine, and they did. And the proper order of things was restored. And I doubt that it took him half a shift to make those changes. So two strokes. If you collect a few exhaust pipe dimensions, there's an excellent Australian book that has all the TZ Yamaha exhaust pipe dimensions. With the aid of that, you can make a pipe that will be close for any cylinder. And similarly, you can get close on port timings. This is not an arcane, secretive cult of unknowable beings in tall, pointed purple hats. It's just stuff we humans do. You can do it too.
Yeah.
And I think that the lessons that were learned in two-stroke GP racing have now found a place to live in competitive snowmobiles and outboard racing and other places where the beat goes on. But of course, the problem with street two-strokes, the reason that after 1984 approximately they disappeared as a road-going vehicle is that there is mixing between the fresh charge and the exhaust, and some fresh charge goes out the exhaust, about 30% of it. And becomes unburned hydrocarbons that are detected by the people up in Ann Arbor. And they say, you can't run that in this country. Clean that model up or be gone. Now, one way to deal with that is to say, oh, we'll put the fuel in after the piston has closed the exhaust port. So that's direct injection. That automatically means no lost unburned hydrocarbons. Another method is to identify that part of the transfer stream that will never reach the exhaust port by the time until after it is closed, and that's transfer port injection. Bombardier builds engines of that type. There are a few European two-strokes that employ these two principles. So the high-power two-stroke is not dead. It's just hibernating.
Yeah, the specific horsepower is still a winner. The weight of the engine it's great. Like if 4-stroke motocross bikes and enduros are magnificent and a lot of fun, and a good 350 KTM or 500 KTM is 4-stroke is a magnificent motorcycle. But then you try a 300cc 2-stroke that they're making also, and you see the light. As Malcolm Smith said, weight is the enemy. Ultimately, weight is the enemy. And he's so right, because you get on a 300 2-stroke and you just think, this is the greatest dirt bike in the world. This is the most magnificent motorcycle for traversing any terrain. It's just magnificent. It really is. So when we're talking about the resonation of the pipe and the waves, we're talking about, you always talk about pipe organ. It's a pipe organ. The pipe makes a nice sound.
Single note.
Plays a single note. A bottle, if you blow across the top of a bottle, the volume of the bottle determines the tone with the air going across the opening. So if you made a
fill it up a quarter of the way and the pitch rises.
Or you change the size of the bottle and it will make a different tone. Big bottle, low tone, got to push a lot of air to make it resonate. And that's what we're talking about with the expansion chamber. It completely changed. It really changed transportation for us. It really made such a simple engine move the world because it was easy to manufacture and
the 60s and 70s were the golden age. Yes.
Yep. And we could make a little bit more smoke back then. We hadn't cleaned our act up yet. And that's what happened to the 2-stroke, as you were just pointing out. It was more difficult to control emissions. You're putting oil in to lubricate. Oil, you had oil injection, or you're mixing oil in your gas, and it's going into, first thing it does is hit those bearings in the bottom end and keep them from locking up.
Yeah.
And but it's also going to burn some of that. So that was our particularly our hydrocarbon problem with the 2-stroke. And that's why when you said to me about my RD 350 and how I said something around 6,000 or 5,000 RPM, and you said, well, you'll find that it won't run particularly well down at that RPM, and you're going to get terrible fuel economy. Because it wasn't keeping all the gas, and it wasn't burning the gas. It would send when it's off of its happy tone,
off the pipe,
fuel's just going into the exhaust pipe unburned.
Yep. And this is why when I first started measuring all the fuel that went into the race bike fuel tank and then measuring the fuel left at the end of the day, I really learned something. What I learned was the greatest fuel consumption occurs in first practice. And I was in Europe in 81 with a rider who had not ridden on those circuits. So he was learning the circuit in first practice. Fuel consumption was high. Second practice, fuel consumption came down a bit. Lowest fuel consumption of all in the race itself. Because once the rider had got the range, so to speak, knew what to do, where the circuit went, how to keep the engine in the power band. Instead of this mixture going out the exhaust pipe, it was being trapped in the cylinder and burned to produce power. Now, reed valves. There has been a lot of talk about how reed valves were going to make this wonderful broad-range two-stroke. It's a two-stroke with two natures. Below the pipe, it is only the crankcase acting as a pump that is moving mixture. So, yes, the engine will run, but if it's a piston port or if it's a rotary valve timed for high speed, at low speed, it will push a lot of mixture back out. So a reed valve improved that situation. It made the engine more drivable below the exhaust pipe resonance. But the actual power band was still determined by the pipe because, for example, when Honda put motocross large area reeds on the cylinders of Freddie Spencer's 1982 NS3 500 triple, power band was 9,800 to 11,000, 1,200 RPM, just like with a TZ750, just like with any two-stroke. Then you start adding devices like the variable exhaust port, timing, exhaust resonators, cooling the exhaust gas in the pipe with water injection to make it resonate at a lower frequency. You can extend the range to a useful extent, but not all that much, which is why when MotoGP began in 2002, the big difference was with a four-stroke, you could start to feed power from the apex, even before the apex, because you could feed gradual, smooth power. With a two-stroke, there was nothing until you opened the throttle a fair amount, and then it started to eight-stroke. Pop, 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 pop. And then to four-stroke, and finally to two-stroke. And at each step, there was a sudden step up in torque. So that's why you saw riders like Mick Doohan holding the motorcycle radically more upright than their own bodies, which were offset into the corner so that there would be enough tire that when the engine hit the pipe, the tire would drive the motorcycle forward rather than spin.
A lot of high sides in those days, right?
In those days, yes. In fact, the FIM told us that if the high sides weren't brought to a close, that they would first impose minimum weights and then intake restriction. Dun, 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 dun. As the AMA had done, was it 78? Sometime like that, at Daytona. Because Kenny had said, we're getting sideways past start finish and something bad could happen. The AMA were chewing their nails. So they only got as far as the increased weight minimum. No intake restrictors for the FIM because the manufacturers responded quickly with torque controls. They simply reduced the amount of torque that was available in lower gears where it's easy to spin the tire, and thereby they limited the hit as the engine RPM rose onto the pipe. And savvy riders like Mick Doohan and Mike Baldwin took care to ride the engine in its linear range, that is, in the range controlled by the exhaust pipe. On a TZ750, that meant between 9,300 and 10.5 or so. Unless you had somebody else's exhaust pipes on there.
Blocking out the entire tack except that area.
Yes. Because it's the area of interest. The idea of trying to dump truck your way off of corners at 6,000 RPM? No, because when you hit 9,300 RPM, the torque is going to double. And you're going to tip over.
Yeah, it spikes so fast. It starts. It becomes. It just goes
can't
bang,
turn it
bang,
backward
bang,
fast
bang.
enough.
Yeah.
Yep.
That was the old Schwantz roll you always talk about. You know, Kevin would have a lot of throttle, and then as the bike is coming in and coming off the corner, he's actually rolling the throttle closed to try and make the torque output more linear.
Even though the power is steadily rising.
Yeah.
rolling it back to keep it from rising too much.
Yeah.
And those primitive torque controls and other electronics of the 1990 period soon were elaborated into the electronic rider aids of the present era. Old timers didn't like them at first. Oh, it interferes with the rider's freedom and it's an existential issue, and let's take several college courses. But then they got to kind of like it.
Yeah. Well, all we've ever...
Fellows at BMW, people on staff who rode but were not competition riders, found they liked rain mode on their new zippity-doo four-strokes because it made them feel more secure. Motorcycle wasn't going to get away with them. Now you see him, now you don't.
Yeah. Yeah, it was a magical time if you weren't one of the riders getting hurt by the motorcycle. But look, I remember going to Laguna Seca, camping at Laguna Seca, sleeping on rocks because we got there late on a hillside in a tent. There were no good campsites left, so we were camping on a hill with rocks on it. And it was sort of 88, 89. I went both of those years, and I would always walk a lap of the track during practice. So practice would start, and I would just walk the entire circuit across the bridge.
I probably saw you then.
Yeah,
I like to do that too.
Yeah, you want to see folks go through 6 at Laguna because it's a neat fast corner. You want to see them drop through the corkscrew, and you want to see between 4 and 5. That's a really neat shoot, and then 5 is a much faster corner than you might imagine. It's kind of banked and it goes uphill at Laguna. And walking between 4 and 5 is when I saw Kevin Schwantz crossed up wheelie, spinning the back tire with the bike's front wheel in the air on his Pepsi Suzuki, weaving between 4 and 5 on the back wheel, driving out of that corner. It was a thing of beauty. Watching who was it? I think it was Ron Haslam on the Kajiva it was Mamola, I think, off into the dirt in 6. Massive tank slapper, broke the windshield, goes back on the bike on the track, heading toward the corkscrew without skipping a beat. Just immediately completely fully tucked in behind a broken windscreen with the throttle backed wide open, like I'm back on pace. I'm going through the corkscrew next. That's behind me.
So it went.
Well, awesome. Yeah, sorry, go ahead.
It has been noted by Ben Spies, who rode in that era, that the extreme torso offset practiced by riders like Jorge Martin and Bastianini would simply not have been possible on 2-strokes because the rider's ability to control the motorcycle was incompatible with having one arm stretched across the top of the gas tank and the other shoulder on the track surface. That kind of the 2-stroke slip and grip corner exit would just shaken the rider off. The rider had to take care to stay on the motorcycle.
Yeah, this reminds. So we were talking about rider aids and the way the power is coming in. All we've sought with all of these electronics is smoothness of application at the lowest traction point. Right, you're trying at maximum lean when you introduce the throttle. You want that to be as perfectly smooth as possible, and it was. This is perhaps another show. We were sitting with Romano Abessiano of Aprilia, and we were talking about he's much like you, Kevin, in the sense that he's a polymath, and as far as engines and things, metallurgy. You guys were talking about rail locomotives and aircraft and this beautiful, you guys just were off on a lot of tangents, and it was beautiful. But what he said was, well, we were starting to talk about the electronics in play on the Aprilia. And he said, well, the first thing that happens is we have a map that takes up the slack in the gear train. The first application of the throttle by the rider has a map that takes up from deceleration to acceleration in the drivetrain.
Normally there would be a clunk there when you first move the throttle. It would go clunk. You don't want that at the apex.
You don't want the clunk. You want that to be perfectly smooth. No, and when we're talking about tiny changes in mass reverberating through the drivetrain, which they are eliminating with electronic controls, with very precise. I mean, it's crazy good. And it's related. It is related to the two-stroke expansion chamber, because what a nightmare it was to try to control that throttle off the apex, and all of that.
Stay within to stay in sync with the organ pipe.
Yeah. Well, thank you very much for listening, folks. This is we're going off the pipe now. We're gonna. We're bogging off the pipe. That's the two-stroke expansion chamber. What a thing! What a change it made to smoky little, dirty little two-strokes to beautiful high specific horsepower and a sound so many of us grew to know and love. I still love it. I have an RD 350. It's time to fly back and make pipes, Kevin.
Making those pipes was good once they were finished. You could look at this smooth shape that you'd made from the exhaust port all the way back to the rear wheel, and not think about the 32 welds, each one of which had to be tapped and hammered and bodyworked into a smooth curve, because what you don't want is an exhaust pipe that looks like the Tin Woodman.
No.
A series of clunky joints. Ugh.
Well, it was who was doing that? There was a company that began hydroforming.
Oh, lovely. Yes.
Hydroforming their expansion chambers, and it made more power to not have the seams and the steps, to have a continuous flow.
Smooth curve, yes.
Smooth curve. It just made more power. You could make the pipe in basically the same dimensions, but the hydroformed one was more better. And
of course, Bultaco had a certain guy, I have his name in notes, who formed the pipes for TSS race bikes from halves. And those halves were hand formed into expansion chamber shape, so that a slight taper from the cylinder, then the megaphone part, then the center section, the convergent, all one piece.
I would like to shake his hand.
Pardon me.
Yes. Yeah, I would like to shake that guy's hand and talk to him, because that sounds exactly like the very troublesome problem that I'm somehow drawn to try to solve. I don't know why. But all right. Well, thanks for listening, folks. And we will catch you next time.